Hey everyone, I hope you're all doing well. So in this video, we're going to be covering part 1 of your first theory quiz review. I plan to cover safety, distillation, and the crystallization labs. Now, the second part of the review session, if you're watching this in real time, will get uploaded sometime Saturday afternoon. I'm just being really meticulous with the questions that I'm picking. For this review session specifically, we have about 22 theory quiz review questions on these 3 topics. So I want to make sure we're getting the practice in, the understanding, and the knowledge, because I really want you to be successful on your upcoming theory quiz. So let's go ahead and let's just start with the very basics, right? So when you had first started lab, you went over safety procedures, okay? Now this is tested on your first theory quiz, so make sure you have a good grasp on it, all right? Anytime you see blue, blue is going to be your health hazard. Red is going to be your fire hazard. One is going, not red, not one. Yellow is going to be your reactivity. And then the white is usually a specific hazard. And then there's abbreviations here that indicate different things. I've never really seen the specific hazards tested, but what mostly is tested is the numbers. So the way the numbers work for these different hazards is the higher the number, the more hazardous it is, okay? So higher number is bad, lower number is good. Okay, and then over here, once again, I just have it listed for you. So fire hazards are red, yellow is reactivity, and blue is health. Okay, and they'll generally be in this same order. You might even see some of these hazards when you're working with chemicals in the lab. Now, there are certain special containers you need to be aware of in the lab, and a few of them are the following. We do have our liquid waste containers, right? Those are those 2 big brown jugs that are in the fume hood, and that's where we dispose of liquid waste. Okay, those are not for water. Those are for chemicals. So acetone, ethanol, any kind of chemicals that you're using throughout the lab that are not water will go in there. If you have water, water just goes down the sink. Okay, waste solids, those guys go into the solids container. That's that garbage pail right next to the liquid waste containers. And that's where you're going to put filter paper, TLC plates, basically anything that is solid with chemicals on it, okay? So if you have a paper towel and you use a paper towel to wipe up a chemical spill, well, then that paper towel now is going in solid waste, okay? That's not going to go in the regular garbage because it does have contaminated particles on it, okay? It has chemicals on it. All right, broken glass, hopefully you know this by now, but if you break something, if you break a flask, a graduated cylinder, a pipette, really anything that's glass, if it breaks, what you're going to want to do, of course, is notify your TA if it falls on the floor or something. If you break a pipette, that's okay. There is a special discarding place for glass, and that is the brown box under any sink. Okay, all the sinks have brown boxes, or at least the majority of them do in each lab, and you just put all glassware in those boxes, okay? If you put the glassware in solid waste or in a regular garbage, you risk one of the people in the lab getting hurt when they take those garbages out, okay? So make sure your glass is always going in that brown box under the sink. Okay, and like I said already, the only substance allowed down the drain is water and soap. So that's about it on safety. Very basic knowledge, nothing too crazy. I do have about 4 practice questions, so let's do them. What I do advise you to do is pause your screen, try the question out on your own, and then resume, and we'll go over it together. So go ahead, pause, try this out, and then we'll do it together. Okay, great. So this is saying during a Chem 327 lab session, you break one of the pipettes you used to transfer a solvent from one flask to another. Where should the broken pipette be discarded? And we can only circle one. So we have a broken pipette, and if you remember, pipettes are glass, right? Pipettes are glass. So with the pipette, you're going to want to put it in the brown box below the sink. So here you should have chosen C for the correct answer. Okay. All right, let's go ahead and let's do the next question. So go ahead, pause, and then we'll run through it together. All right. So the National Fire Protection Label for 1-butanol is shown below. Which of the following is the best summary of the label's meaning? Okay. For questions like this that are multiple choice, I like to kind of establish what's going on in my own head when I look at this before I look at the answer choices, because I get confused easily, right? My brain kind of runs all over. So when we're looking at this, we know that blue is health. We know that red is fire or flammability, right? And yellow, that guy, which isn't really showing up, so I'll write it in green, that's reactivity. Okay, so right away, reactivity is 0. That tells us that it's pretty stable, right? It's not going to be reactive. Okay, start with the easier numbers. So it's not going to be reactive. Let's eliminate all the choices that have this as being a reactive compound. Okay, so A is saying it's unstable. That's incorrect because it has a 0. This is a pretty stable. Gone. Let's see. B is saying we are highly explosive. Yeah, nope, we're not. C is saying we're explosive, but we're not. D is saying we are stable. We're going to keep that guy. E is also saying we are stable, and so is F. Okay, so just by looking at this one side, we can already get rid of the other choices. Now let's go ahead and let's take a look at fire. Fire is a 3 rating. That's pretty high. So we are going to say that this is a flammable substance, right? Does everybody agree? This is flammable. Fire is at a 3, okay? So 1-butanol is flammable. It's also stable. So based on that conclusion, we can go ahead and eliminate D, and we can also eliminate E. So it gives us our answer, but let's just confirm it by looking at health. So health is at a 2. That means that it's not a super heavy health risk, but it is pretty dangerous. Okay. Okay, sorry about that. My camera's been a little glitchy, so my webcam turns off occasionally. So as we were saying, we're still going to confirm F. So with the health hazard, it is at a 2, so it is still dangerous to your health. Okay. So in this case, you should have gotten F as the correct answer choice here. All right. Now on your actual theory quiz, I'm only expecting you to get one of these. This is usually what I like to call a give me question, because the info is not too crazy. As long as you have an idea of what's going on with these numbers, you're pretty okay on these questions. And it's a nice 3 to 5 points, depending on how much it's worth. All right, let's go for the next one. Go ahead, pause and try this on your own. All right, so there's a solvent that's known to have a significant health hazard, to be highly flammable, and it's normally stable. Choose the NFPA label. So let's break down what they're telling us. Significant health hazard, highly flammable, and it's normally stable. I always like to look at the stability ones first, because it's either like really unstable or it's really stable, right? So really stable means that we're going lowest number possible, so we're going 0. 0 or 1, right? It's normally stable, so let's go 0 or 1. So that leaves us with A, B, C, D is out, E is here, and F is out, okay? And once again, stability is going to be this guy here, okay? Those guys in yellow, that's your stability. And the lower number is more stable. We are also told that this compound is highly flammable. Highly flammable means the red one has to be a big number, right? So if red has to be a big number, I'm getting rid of A, because if we're highly flammable, we're going to be higher than 2. Okay, like this guy has a 4. Definitely could still be B. C's out. It's definitely not 1. Okay. And then when we look at E, E is also at 4, so E is also still in. All right. So now we're between B and E. So we are told we have a significant health hazard. Health hazards are blue, and significant means there is a present health hazard, right? We have to be careful around this. So which number is bigger in blue, B or E? And the correct answer here is choice E, okay, because our health hazard is 3. All right. Go ahead, pause, and try this one out. And this is the last one that we have on safety. All righty. So when we are looking here, we are told isopropanol, hydrogen peroxide, and propane gas are common household chemicals. Based on the labels below, choose the correct statement. So this has a lot going on, right? There's a lot of information to keep track of. So the best way to do this kind of question is digest it piece by piece, okay? Choice A says isopropanol has the greatest health hazard. Well, health hazard is blue. So who has the greatest health hazard? Hydrogen peroxide. So I'm just going to write a little note. Greatest health hazard, just so I don't forget that. So A is out. B then tells us hydrogen peroxide is explosive. So now we're referring to the stability of the compound. And I would agree, it's definitely possibly explosive, right? Because the reactivity is at a 3. So I'm also going to put explosive, right? Or relatively unstable. All right. Choice C. Wait, we're still on B. My bad. Isopropanol has the greatest health hazard. That is incorrect, right? We already said hydrogen peroxide has the greatest health hazard. Then we go for C. Propane is the most flammable. All right, so flammable, we're looking color red, highest number. So out of these 3 options, hydrogen peroxide is not flammable at all. However, isopropanol has a flammability of 3. Propane has a flammability of 4. So propane is the most flammable. That is a correct statement. Hydrogen peroxide has the greatest health hazard. Yes, also correct. And it is explosive. Yeah, 100%. So it's looking like C is going to be our answer here. Let's just check the rest to be sure, okay? So for letter D, isopropanol, greatest health hazard, that is wrong. Hydrogen peroxide, greatest health hazard, that is correct. Isopropanol is the most flammable, that is incorrect. And for F, propane has the highest health hazard, that's also incorrect. Okay, so for this question, you should have gotten C. Now let's go ahead and let's dive on into the first lab that we had covered in this course. And that is going to be the distillation lab. So the distillation lab is what you had done on your first day when you checked in, okay? So let's just do a little review of distillation, what it means, how it works, things like that. So here's the definition for distillation. It's just the process of heating a liquid to its boiling point. Then you capture that, you cool the resulting vapor, and then you collect the condensed liquid. It basically comes back down into that liquid form and it drips into your graduated cylinder, right? So this is where you use that micro distillation apparatus, okay? Things we could use distillation for: identifying organic compounds. And the reason we can do that is because through distillation, we can actually take the boiling point of these liquids that we're boiling off. And you can also use it to separate organic compounds, right? So when you're separating organic compounds, you generally want a boiling point that is greater than 50 degrees in order for this to work. But what this does is it allows you to separate 2 or more liquids in a mixture. That is called fractional distillation. And fractional distillation is actually what you had done in your lab, right? Where you have your 2 mixtures and then you're separating them and you're taking fragments of each, okay? Just the definition for boiling point here: temperature at which vapor pressure of liquid equals the external pressure. External pressure is usually the atmospheric pressure. And now let's take a look at this guy. So lowering the pressure lowers the boiling point, okay? And this is most commonly seen in vacuum distillation. And you had done this technique in the roto evaporator, okay? So the roto evaporator is what you use in the Trine-Riston lab. And that actually works with vacuum distillation. So just a nice little connection there between the labs. All right, phase diagrams. I must say, in this course, I think phase diagrams were my most hated topic, only because for the life of me, I couldn't understand them. And then the day I understood them, I was like, holy crap, this is great. I can do a phase diagram. Like, what does the world come to? You know, these things are scary, okay? So just a few things here. I got these directly from Dr. Katsamanis's lecture, so you may be familiar with them already. But this is what a phase diagram looks like. It has a liquid curve and a vapor curve, okay? And then it has a bunch of values and a lot of numbers, things going on, letters. So the x-axis, this guy here, this is representing your different mixtures, okay? Your y-axis is your temperature. So that's like your boiling point. The lower the boiling point, the higher the vapor pressure, okay? Now, the liquid is the bottom curve and the vapor is the top curve. The vapor is also called the distillate. So you'll see a lot of theory quiz questions ask you for the percent distillate collected, and you have to know that percent distillate is equivalent to the percent of vapor, okay? All right, so this is just what they look like, and then I'm going to show you a couple clicker questions he had. We're going to do those, and then once we're done with distillation, I have more phase diagrams from previous theory quizzes. So here we want the composition of the boiling liquid at 100 degrees Celsius. So it's asking for the composition. So it wants the percentages, right? It wants to know how much is A and how much is B at 100 degrees Celsius. So what I'm going to do is I'm going to take my marker. I'm going to go 100 degrees Celsius right there. And then we're going to go straight across. And they are asking for the boiling liquid. So we're asking for a liquid. So now I can go ahead and go down. And if you take a look at that, let's see, we fall about 75% of B, right? So if you take a look, they're asking for the percent composition of A. So there's a few different ways we could answer this. We could say that this is 75% B, right? Because B is on the bottom. Or we can also say that this is approximately about 35% A. And because they're asking for A, the correct answer here would be D, okay? So they'll usually tell you which one they are asking for. Now, when you're doing these kinds of questions, occasionally there'll be short response and not multiple choice. If that is the case, just as long as your value is within about 5% of the accepted answer, you'll still get credit for it, okay? They're not super cruel when it comes to that. All right, let's keep going. So now we want to know the composition of the vapor above the boiling liquid at 100 degrees Celsius. So the way this works is we know that at about 35%, right, that was 100% of A. So I'm going to go ahead and draw a nice line. Okay, let me see if I can give it a better color. Maybe white will be better. Yeah, look at that. So we have 35% A at 100 degrees Celsius. Then you just want to come over straight as you can and go straight down as best you can. Okay, so I feel like that's really not the best drawing I could come up with here now, is it? So we go about there-ish, and then it comes about here-ish. Anyways, hopefully you're getting the point that you just take this guy, draw a line to the vapor curve. As soon as you hit the vapor curve, you want to come straight down. And here, in terms of A again, we're at about 75, 80% A. And the answer choice that we're going for here is B, 75% A. Okay, so here they're asking for the composition of the vapor above the boiling liquid. They could have also asked for the amount of distillate. Distillate. Okay, let's keep going. So using simple distillation can be used to separate compounds with different boiling points. I already said, you definitely want to have a greater than 50 degrees Celsius range between them. The more distillations you do, the more chance of purity. And then in his lecture, he slightly described azeotropes. Just know that a positive example of an azeotrope is ethanol. They can be positive or negative, but a positive azeotrope is ethanol. And that's generally why in lab, you'll see that it's composed of 95% ethanol, because about 95% ethanol is as good as it gets when we do the distillation on it. All right. So with distillation, we also relied a lot on boiling point. There are 3 factors that influence boiling point. They are molecular weight, polarity, and hydrogen bonding. Okay. If you previously took Organic Chem 1 like you're supposed to, or if you're taking it with this course, hopefully you got up to it already. but molecular weight, polarity, and hydrogen bonding. You can kind of say that these are in order from not really mattering to the best, right? So we definitely value hydrogen bonding over the other two, okay? Now, I know polarity sounds a bit weird, and I'm going to describe these factors in more detail. So let's go ahead and let's do that. So when we're looking at molecular weight, as the molecular weight of the compound increases, the boiling point increases. Okay, and that's seen here between butane and octane. You'll see that the molecular weight goes from 58 to 114, and that boiling point also increases substantially. Okay, so that's just one factor that can contribute to boiling point increasing. The other factor is polarity. Now, polarity, it's kind of a weird topic the way it's discussed, because normally we think of polarity as like this big extravagant word, right? It's like, what does polarity mean? We're talking about different forces, okay? So we could say this first guy has dispersion forces, right? This second guy has a dipole-dipole force. And the third one has hydrogen bonding. So if you remember from the boiling point lectures when we took organic chemistry 1, right? Dispersion's like the worst force to have because it's in everything. Dipole-dipole is better than dispersion, which makes sense because the boiling point of this compound is higher than that compound, okay? And then same thing here, we have the hydrogen bonding going on. So that's substantially higher, okay? So when we talk about polarity, feel free to use intermolecular forces to help you explain it to yourself a little bit better. And then the last thing we're going to talk about in terms of boiling point is hydrogen bonding. So very quickly here, because I do want to get to these questions. When we're looking at hydrogen bonding, right, we have one hydrogen bond there, the boiling point 78, okay? Then you go to having 2 hydrogen bonds, you jump to 197, all right? And finally, you have 3 H bonds going on. Now you're jumping to 290, okay? So hydrogen bonding is super important when it comes to determining boiling point, okay? Of course, depending on the structure, the jumps and the differences could vary, right? Like if you take a look at these two here, you'll notice that this structure has the higher molecular weight, but this structure has the higher boiling point. The reason for this, once again, we have hydrogen bonding occurring, which makes the boiling point slightly higher than this structure here, okay? So just be aware of these different factors. So now that we've covered this a little bit, let's go ahead, put our knowledge of boiling point to the test, and let's do a question. So pause your screen, try it out, and then come back. Alrighty, great. So hopefully you had a chance to try this one out. Now, the first thing I'm going to say here is I'm not going to go and count the molecular weight for all of these, right? I don't have that kind of time or patience to count all the hydrogens and stuff. So what I do suggest doing is first looking at hydrogen bonding or the polarity of these compounds, okay? So A is acetone, and A has that dipole-dipole interaction. B has dipole-dipole. C has dipole-dipole, but C also has hydrogen bonds. Okay, it's like the magic winner. All right, so when you're looking at these, D like has nothing going on, she's pretty sad, and E has dipole-dipole. So when you're looking at this, C is going to be higher in boiling point, okay? That I thought was just a fun review question on boiling point in case it gets tested, okay? Alrighty, now 9 out of 10 times you are tested on those distillation curves, so just make sure you are familiar with them, okay? And we're gonna do a few questions in just a moment. Now, in the distillation lab, there was a particular setup we had to be comfortable with. So let's review that setup just a little bit. Your setup should have looked something like this, where you had the following tools at your disposal. You should have had your heating mantle. It should have been plugged into a variac, right? So you have to make sure your heating mantle is plugged into a variac, because with the variac, we can control the heat setting. If it was connected directly to the outlet, it would get too hot. We wouldn't be able to control the heat. So having it connected to a variac is very important. We also had this iron ring on the bottom, and that's what supported our heating mantle. Okay. All right. Now, the next thing we had to do is you had to make sure that you put a boiling stone inside the RBF, the round bottom flask, right? Because if you set everything up and you forgot the boiling stone, you had to take all of this off, open it back up, right? Find the boiling stones and then put one in. So definitely don't forget that there should be a boiling stone in here, which in this image you can't see, but just so you have the knowledge of it. You want to make sure that the neck of the RBF is clamped, right? We clamp the neck of the RBF so that everything is a stable foundation, just in case if this were to fall or when we remove it later, the RBF is still safely in place to, you know, it's a safety risk, right? We want to prevent the breaking of glass and things like that. Okay. Then the next thing we wanted to do is your RBF. It should have been about a third to a half full, right? If the liquid line was up here, it would be way too much. It would be overfilled. You'd have to get a bigger RBF or you'd have to figure something out. Okay. All right. Then from there, you had to go ahead and set up your micro distillation apparatus, which is this guy here. Once you greased your joints, you connected them, you then put your thermometer inside. Now you should have also had your O-ring inside here, right? Your O-ring should not have been on the outside. One thing that is not pictured in this diagram is that Dr. K requires that you also have the thermometer resting on a clamp. So rest thermometer on a clamp. Okay, make sure that's something that you did. And in the lab or the theory quiz, if it's asked about, make sure that you mention, you know, you have to clamp the thermometer, things like that. Okay. Now, the thermometer, it is not allowed to touch the glass. Why is the thermometer unable to touch the glass? Because the glass is going to get very hot, right? So if the thermometer is touching the glass, it can provide us with inaccurate temperature readings. So we want to be super cautious of that. The next thing, and probably the most important part of this experiment, was the positioning of the thermometer itself, right? Because if your thermometer was too low or too high, it was going to skew your temperature results. So if we zoom in here, you'll see that we have the temperature bulb. And what you want is you want the top of the bulb to be level with the bottom of the sidearm. Okay, and let me just write that out. So we want the top of the bulb level with the bottom of the sidearm. Okay. I hope so far this is proving to be helpful. I really just want you guys to do well on this theory quiz. Alrighty, water out goes on top, and then water in goes on the bottom, okay? And this one's open to air. You also had your graduated cylinder, and your drop rate should have been about 1 to 3 drops per second. Anything more than that, it'd be a little too fast. Just make sure that you never distill to dryness, okay? Make sure to always remove the heating mantle before your RBF is empty. All right, I think that's everything I had to say on this slide. So let's go ahead and let's move on to the next slide here. This is what we were talking about earlier, just a little bit with that fractional distillation. So this is just some information on it. But essentially, this is the experiment that you had run in your lab. So you had your 2 compounds. You should have had a little bit of forerun at the beginning. And then this first plateau here, that's the boiling point of the first liquid you're collecting. Okay, so maybe this liquid has a boiling point of, I don't know, 57 degrees Celsius, right? That would be this guy here. Then once almost all of this has burned off, you're going to see the temperature start to rise again, and it'll be a second forerun. And maybe the boiling point of this liquid is like 120 degrees Celsius. So then once it reaches its plateau, that's that liquid being collected, right? And ideally, we say that these are the pure forms of these liquids, okay? All right, So let's keep going because I now have some questions for you guys. I think we have about like 4 or 5 questions on distillation, which is pretty cool. Majority of the questions are on crystallization just because there were so freaking many. And I was like, all right, we have to do them all. Like we have to make sure we're prepared. We need to kick this theory quiz's butt, you know? So here, pause this video, try this question out, and then we'll run through it together. All right, let's do this. So here we want to list 3 things that are incorrect about the simple distillation setup shown below. So there are 4 things in total wrong with this setup, but they're only asking for 3. Okay, so if you have any 3 of the 4 that I write, you're good to go. So we just reviewed this, so hopefully it stuck. So what we have here is I'm going to go, all right, I have my iron ring, right? I have my heating mantle. That's good. Heating mantle is connected to variac. Excellent. I have my RBF. And the first thing I notice right away is that this isn't clamped, right? Where's the clamp for the RBF? That's not safe. It's not going to stay in position. This could fall over, right? This is an expensive piece of lab equipment. We do not want that falling over. So right here, we could say that there's no clamp on the RBF. No clamp on the RBF or the round bottom flask, okay? The next thing I notice right away is the round bottom flask itself. Look at that liquid line. That's more than half full. That's dangerous. So the liquid is more than half full. That's another error. Okay. Now, hopefully there are 2 more errors. Hopefully you were able to point them out. The next error I notice is the thermometer, right? The thermometer is incorrectly placed. The top of the bulb needs to be level with the side arm. Okay, and the very last thing that is wrong with this setup for simple distillation is the thermometer is not resting on a clamp, you know, or some kind of surface. Okay, so those are the 4 things that are wrong. Just as long as you came up with 3 out of these 4, you're okay. All right, you get full credit, you get all 4 points. All right, so let's kick things up a notch and let's go for those phase diagrams. Okay, and let's up the difficulty level here just a bit. So questions 1 through 3 refer to this diagram. I think I just have the first 2 on here though. So let's go ahead and let's do it. So we are told that we have a vapor liquid equilibrium diagram. And did I not erase it? Good. So you guys are going to pretend that you never saw that. Maybe you didn't even notice it, which is great. But let's go ahead and let's take a look. So here we want to know which solvent has the lower boiling point. Okay. So remember how these curves work. The liquid is the bottom, and the vapor or the distillate is the top. So we want lowest boiling point. When I look at my x-axis, here's what I'm gathering from the information given. We have chloroform and dichloromethane, okay? Over here, we have 0 chloroform and essentially 100% dichloromethane. Over here, we have 100% chloroform and no dichloromethane. So what does that mean? That means the boiling point of chloroform is 61 degrees Celsius, and the boiling point of dichloromethane is 40 degrees Celsius. So which solvent has the lower boiling point? That's going to be dichloromethane. Okay, I hope that makes sense to you. Okay, our next question is, if you distilled a mixture of chloroform and dichloromethane that was 60% chloroform, what would the approximate expected composition of the distillate that you collected? So they're telling us we have a mixture. Mixture is referring to liquid, 60% chloroform, Then we want to know how much distillate did we collect, which is asking us how much vapor are we collecting. So we need 60% chloroform. So now you have to decide which 60% to use. We want 60% chloroform, so we want to use this one, okay? So we have 60% chloroform. That's the liquid curve, right? We want to go to vapor. So then we come across until we hit the vapor curve, and then we come back down. Okay, that's how we draw that one. Now they're asking for the amount of distillate we collect. If you look at the answer choices, they want the amount of dichloromethane. So all you're going to do is say, okay, dichloromethane's on the bottom. Let me ignore the top row. And it looks to be in between 60 and 80. So I'd say about 70 or 75%, depending on how accurate the lines are that you're drawing. Okay, and that is one of our answer choices. That is choice E, and that is the correct response here. Okay, so those are big, scary phase diagrams. We got another one for you, so let's do it. Questions 2 and 3 refer to the vapor-liquid equilibrium diagram. So go ahead, pause it, try it out, and then we will review it together. Okay, great. So here they want to know which solvent has the lower boiling point, propanoic acid or propanol. Now, looking at this when I first did it, I had a mini panic attack because all I see is propanol on the bottom, right? There's no A and B. It's not like the other one where it was separated into two. But then I was like, okay, this is fractions of propanol, right? So if propanol is 1 over here, that means this is the maximum amount of propanol that I can have. So that means that this side is propanoic acid. Okay, that's how I thought of it when I was looking at this question. So who has the lower boiling point? Well, the lower value is over here. So it would be propanol. Okay. Because here we have 100% mole fraction of propanol. So that's how I got 97 as the lowest, meaning that propanol is the lower boiling point. All right, now they want to know the composition of the vapor that forms when a 1-to-1 mixture boils, and they want it as a percentage. 1-to-1 mixture, that means half and half, right? So you're going straight for the middle. So looking at my x-axis, this is 0. And then you have like 0.1, 2, 3, 4, 5, 6, 7, 8, 9, and then 1. So we need a 1-to-1 mixture. So we need to go for the middle here. So 0, 1, 2, 3, 4, 5, right there. So that's the middle. So that's our 1-to-1 mixture. Now we're going to go straight up to our liquid line. We don't want liquid, we want distillate. So we come on over to the vapor line, and then we come back down. Okay, and what number are we at? Well, if this is 1, this is 0.9, this is 0.8. So we are at 80% vapor. Okay, I hope this is making sense to you all. All right, let's continue down the road of fun. I think this is, this is question number 3 that belonged with this guy. So I had it out of order. Oopsies. But anyways, let's go ahead and let's take a look at it. So if the data on the vapor-liquid equilibrium were collected under a reduced atmosphere, so if we lower the pressure, what's the difference with the diagram above? Okay, do you guys remember what we said about pressure and boiling point? What happens to them? Anybody? Anybody? You guys remember? Hopefully you remember. So we said that if you lower the pressure, you lower the boiling point, right? So if we're lowering pressure, well, then the liquid line is going to be lower, causing the vapor line to be lower. Okay, so that one's just like a cute little fact you have to remember. It's a cute fact. So vapor lines, liquid lines are lower. When you lower pressure, you lower boiling point. Okay. Alrighty. Go ahead, pause your video, and try this next question out. And I believe this is the last one I have on distillation. Alrighty, so at the end of a distillation, the distilling flask is almost empty. What's the first thing you should do? So you're done with your distillation. The distilling flask is almost empty, which means our RBF is almost empty. So what should you do? Because remember, we should never distill to dryness. So your first course of action would be to remove the heating mantle. Okay, the heating mantle, that is your source of heat, right? That's what's powering this whole system essentially. So if you remove the heating mantle, what that will allow the system to do is cool down, okay? If you turn the variac off, the heating mantle is still warm, right? You guys ever cook eggs, right? Well, I used to suck at cooking eggs. And then I realized my problem was that the pan gets hot enough so the eggs still cook even with the flame off, right? So think about pots and pans, right? You turn the flame off, but the pot's still hot. You're still going to burn yourself. It needs some cool down time. Well, the same thing goes for the heating mantle. It needs cool down time. So that's why it's the first thing we want to remove. Okay. All righty, everybody. We are doing so great right now. Let's go ahead and let's move on to crystallization. So crystallization, here we go. This is the lab that probably made you lose your mind. Back in the good old days when I took the class, the crystallization lab was actually the first lab that we got to do. So we did check-in, and then we came in the next day and we did crystallization. And as a new student, not knowing where anything was and already having anxiety attacks before the lab period started, having this as your first lab, it really just makes you want to cry a little bit on the inside. And I most certainly did. I cried in the middle, beginning, during, after. I still cry to this day when I think about it. Anyways, let's get to the info. So we have large scale crystallization. That's used to purify solids that are mostly pure, and that's the crystallization method that we're using in this experiment. We're using large scale crystallization. In dry Maristan, we had used small scale crystallization. In the crystallization experiment, this is where we use that logic of like dissolves like. Okay, so you want something that is soluble at hot temperatures and insoluble at room temperature. Okay, all right. Let's see if I missed anything. Nope, we're good. All right. So here I just have a short summary of the procedure that you followed. First, you found a suitable solvent. Those were your solvent trials, right? You had to pick between, I think, toluene and Lagroin, and ethanol. Those were the three. Then you used water. We used water because it was the best solvent for this experiment. Okay. From there, you went ahead and you dissolved your crude product in a minimum amount of hot boiling water or solvent. Once you had dissolved it all, you then performed hot filtration. Now, I want to focus on hot filtration for just a moment here. As you'll see, I have two setups depicted. These are both the hot filtration setups. Okay, this one's on a hot plate from your lab. This one's on an old school hot plate. They're the same exact thing. I just couldn't pick which picture I like the most. Okay, I like this one because you can kind of see the crude insoluble impurities there. And then here it's just the fluted filter paper. So with hot filtration, you used a beaker, you used fluted filter paper, you used a stemless funnel, and a hot plate. In hot filtration, remember, the goal of hot filtration is to remove insoluble impurities. Those terms get thrown around a lot, so let me explain. When we're talking about insoluble impurities, that means that when we add the liquid, right, the bad stuff won't fall through. We're hoping only the good stuff comes through, the crystals that we want to make, the crystals we want to collect. So this yellow that you see, that's all the bad stuff. That's the impurity that's in the crystal. Okay, that's what we're trying to get rid of from the crude mixture that we had started with. Okay, so what happens is when you use a stemless funnel, when it doesn't have a stem, It minimizes the amount of surface area. It minimizes the amount of crap the product is going to touch on its way down. Okay. Now, the more surface area you have, the more likely it is that the crude product is going to come out of solution. And that's going to cause a problem for us. Because now, not only is the insoluble stuff getting trapped, but those soluble bits that we want to fall down, well, now they're stuck to the inside of those stems. Okay, so that's going to lower our product yield. So that's what we want to do there. In order to maximize our yield, we did rinse a few times because that removed the soluble portions, so that way they could fall right through. Okay. After we performed hot filtration, we cooled. Remember that when you cool, you want to cool slowly. If you cool too fast, you're going to have a lot of impurities. So you want to cool nice and slow. Okay. Then toss that sucker in an ice water bath and your crystals will form. From there, you want to perform vacuum filtration. This should have been what your vacuum filtration setup looked like. You should have these filter flasks, your trap adapter. You should have your Buchner funnel. And if you look ever so closely, you'll see that there's a filter vac underneath the Buchner funnel. Okay, you definitely want to have that filter vac. That prevents the Buchner funnel from coming into contact with the glass and potentially breaking. Okay, it also keeps the vacuum system closed really nicely so that you get really good suction. So we said slow cooling gives better results, larger and pure crystals, excellent. Blah, blah, blah. Okay, vacuum filtration. This is probably the most important part and the most confused part. Vacuum filtration gets rid of impurities that are soluble. So it removes soluble impurities. Vacuum filtration removes soluble impurities. Very easily confused with hot filtration because hot filtration removes insoluble impurities. So make sure you know those differences, okay? Hot filtration removes the insoluble. Vacuum filtration removes the soluble. Easy way to remember it. Hot filtration, right? The junk that gets collected on top gets discarded. We throw it in the solid waste container, right? We keep the liquid. So these are insoluble because they didn't go through. Vacuum filtration, you're removing soluble impurities because you're collecting the solids that are inside the Buchner funnel. You're disposing of any liquid, right? Does that make sense? Okay. When you wash, you want to wash with cold solvent. You want to make sure that you open up the vacuum first. Your first step should always be to break the vacuum open. Once you break the vacuum open, you want to go ahead, pour your cold solvent. Then you could use a spatula if you want, just kind of move it around, get the cold solvent everywhere. Then that will really wash your crystals real nice. From there, close the vacuum back up and let it do its thing. Okay. Alrighty. So I believe that is everything I have on crystallation. I think I have about like 10 crystallation questions. So let's go ahead and let's start going through them. All right. So first crystallization question, here we go. Pause this video, try it out, and then we'll run through it together, everyone. All right, so select the true statements concerning the washing step towards the end of a crystallization procedure. So we are talking about the washing step towards the end of a crystallization procedure. So the washing step, which apparatus is that? That's vacuum filtration, right? We want to perform this via vacuum filtration. So with vacuum filtration, I'm going to put VF for vacuum filtration. You guys remember, was it soluble or insoluble impurities? Good, soluble. Right? Vacuum filtration, we're removing soluble impurities. So let's read through these choices. Number 1, the purpose of this step is to remove impurities that are soluble in the crystallizing solvent. I love it. It's got our word in there. Sounds pretty darn good. Let's keep going. The purpose of this step is to remove both soluble and insoluble impurities. That is an incorrect statement. Any insoluble impurities should have been removed during hot filtration. Next up, before the washing steps, the collected crystals should ideally be allowed to dry to expose the impurities. That doesn't make any sense. Okay, that's a crap answer. And last but not least, the washing solvent should be cold to minimize redissolving the crystallized product. That is also a correct statement. So here are the correct answers that you should have chosen are 1 and 4, so C. Okay, so we definitely want to do the wash step to remove soluble impurities, and you want to use cold solvent. If you use hot solvent, you're going to redissolve those crystals. So you must use cold solvent, okay? All right, go ahead and try this one out. All right, so this one is definitely a lot to take in. So it's saying to use the following data to answer questions 7 and 8. The real question is, did I put a question 8 on here? And I did, go me. Eleni and Rishi performed solvent trials on compound X in order to determine which solvent to use towards large-scale crystallization of a crude sample of compound X. Okay, so they're running solvent trials, right? So they're taking a bunch of liquids and they're trying to figure out who's the best. So our question is, which of the following 4 solvents would you expect to be least likely to fully dissolve compound X at boiling temperature? Pick one, then explain why. Okay, so we got a lot going on here. Let's digest this question nice and slow. So we got acetone. Acetone has a boiling point of 50 degrees Celsius. At room temperature, it is partially soluble. Well, if it's partially soluble at room temp, it's probably partially soluble at boiling, right? It could be a mix of both. So right now, this is probably least likely, right? Just for the moment. Let's see what else we have. Now they're telling us room temp is 25 degrees Celsius, by the way. We are told diethyl ether has a boiling point of 35 degrees Celsius, insoluble at room temp. Hexane, 69, insoluble at room temp. And water, 100, insoluble at room temp. This question, you kind of have to think a certain way. So when I say, okay, the room temp's 25, right? Partially soluble, insoluble, insoluble, insoluble. When I look at the boiling points of the liquids, this one stands out to me the most, as does this one, right? Because this one's super duper high. This one's super duper low. Now, water boils at 100 degrees Celsius, right? We know that. And it's insoluble at 25. So at 100, it might boil, right? It might solvate. Diethyl ether has a boiling point of 35 degrees Celsius. Now, room temperature is 25 degrees Celsius. Can we agree that that's not a big difference between these two? Right? That's 10 degrees. That's nothing, right? So if this is insoluble at room temp, what's the likelihood it's going to boil when we crank up the temperature by 10 degrees? Right? Highly unlikely. So for that reason and that reason alone, in this question, we can say that diethyl ether is least likely to fully dissolve compound X at boiling temp. Okay. Acetone is a good runner-up in a sense because it's partially soluble at room temp, so it won't, dissolve everything at boiling point. It will dissolve some of it, but the best answer is diethyl ether. Okay, and let's explain why. So because the room temperature and diethyl ether have a small difference in boiling point. Sorry, my handwriting sucks. And boiling point. We don't expect to see any differences, okay? We do not expect the solubility to be different between the two? Solubility to be different when boiling, sure. We'll add a little pizzazz. Right, so something along those lines would get you credit here, okay? All right, so that's question 7, and that was worth 5 points. Now let's go ahead to question 8. So question 8 is a continuation of question 7, and go ahead, pause, try it out, and then we'll run through it together. All righty, so we are told, Eleni and Rishi choose the same solvent to perform a large-scale crystallization of compound X. Good for them. They each observed a significant amount of crude sample precipitate out onto fluted filter paper during the hot filtration step. Okay, so the crude sample precipitate out onto the fluid filter paper. So that means there's a lot of yellow stuff on their filter paper, right? Think of it that way. So filter paper has a lot of stuff. Rishi pours a more fresh hot solvent over the sample in small portions before allowing his filtered hot solution to cool. And Eleni just moved on to the cooling step. The rest of the experiments perform the same. What's the major difference in their final results? Well, let's talk about hot filtration for a moment, right? What did we say hot filtration does? Hot filtration removes insoluble impurities, right? That's its purpose. Now, when you perform the wash step, do you guys remember what happens with that? When we perform the wash step, we're increasing our yield. So the major difference we expect to see is because Rishi performed the wash step, Rishi's yield of compound X should be much higher than Eleni's. Okay, that is the major difference that we should expect to see when looking at their results. Okay, that's the best answer choice. All right, let's go ahead and move on to the next question. Pause, try it out, and then we'll run through it together. Alrighty, guys, let's run through this. So during the crystallization experiment, a student conducted solvent trials using pure benzoic acid. The results are shown below. Solvent C is the best according to these results. What would be the effect of using B instead of C? We can only choose one answer here. So let's see what we got, right? So solvent A, we have insoluble at room temp, insoluble at boiling. So obviously wrong choice, right? A is definitely awful. Now I know they tell us this already, but I feel like going through the info for yourself makes sense in your head, helps you understand the question a bit better. B, we have it as partially soluble at room temp. At boiling, it's completely soluble, and it does precipitate, okay? Shows precipitate. And then C, we have insoluble at room temp, soluble at boiling, and then we see precipitate. So yeah, C is definitely the ideal scenario, right? That's the best liquid for us. That's the best solvent for our crystallization experiment. Now, what happens if we don't use C and we use B? Well, first of all, can we agree that F is just crap? Trick question, solvent A is the best. That's no, never pick that. Bad, bad, bad. Okay. So if we use solvent B, some of it's gonna solvate at room temp. So that means by the time we get to boiling, we're gonna have less crude product. Does that make sense? Because some of it was already gone, right? It's already mixed in. So at boiling, we're gonna have less crude than we would if we used solvent C. So right away, our yield is going to be much lower, okay? If all the following steps are followed exactly the same by the student, which they should be, right? Find your solvent, you run hot filtration, vacuum filtration, wash steps, all that stuff. The purity should be about the same. You know, you can get different yield, but have the purity be the same. So in this case, we are going to have the yield be much lower, but our purity is not going to change because the rest of the lab should be followed appropriately. There's nothing to indicate that it's done incorrectly. So let's see where we are told that the yield is less. In D, The yield of the crystallized product would be lower, but there would be no significant difference in purity. Okay, that's definitely the one we want to go for. Okay, please make sure you're trying out these questions on your own before I go over them with you. See if you can kind of get a sense of where these are going. Okay, it's really good practice for you. All right, go ahead, pause, and then we'll run through it together. All right, so Chem 327 student ran out of time during the crystallization experiment and skipped the vacuum filtration step. Instead, he lets the water evaporate over the weekend until his crystallized benzoic acid is dry. What's the most significant effect and why? All right, guys, what is the point of vacuum filtration? Y'all remember? What are we removing? To remove soluble impurities. Good. So if you do not perform vacuum filtration, you are not removing soluble impurities, which means that we're going to be more pure or less pure. Right, we're going to be less pure. Okay, so the yield doesn't matter. So let's take a look. The product would be less pure. A is a valid answer. B is not. C is not. D is not. F's not. So now the difference between A and E comes down to, do you remember which soluble to use? Okay. Insoluble impurities, that's hot filtration. Soluble impurities, that is vacuum filtration. Okay, so you should have picked E for this one. All right, let's move on to the next one. Chem 327 student performed a large-scale crystallization of 0.410 grams crude benzoic acid. At the end of the experiment, the percent recovery is 65%. How much pure benzoic acid did she obtain? No need to show your work. Give your answer in grams. All right. So go ahead, try this one out, and then we'll run through it together. All right, let's do this. So hopefully you remember for this experiment, it should be the pure over the crude times 100%. Okay, so when you're doing this experiment, my laptop's dying. When you are doing this experiment, the crude is what you start with, right? The pure is what you obtain. So we are told we have 0.410 grams of crude and the percent recovery is 65. So we have to find the pure. So we're finding X, right? The crude is 0.410 and we're getting 65%. So 0.65. So all you have to do here is a little bit of math, right? Multiply these guys. So we get 0.410 times 0.65 equals X. That tells us when you do the math, X is equal to 0.267 or 0.27 grams, however many decimal places your heart desires. Okay. And that's it. That's all we want to do for this one. So how much pure benzoic acid did she obtain? 0.267 grams of pure benzoic acid. Please make sure you bring a calculator with you. Okay, they will not have extras. They won't let you borrow anyone's. So make sure you bring a calculator with you, okay? Just for simple math like this. All right, it's nothing too crazy. All right, let's try the next one. Go ahead, pause, try it out, and then we'll walk through it together. Alrighty. During the crystallization experiment, you performed solvent trials in part A. Which of the following are valid or is a valid reason for not selecting a certain solvent? Ooh, so now they want to know why we wouldn't select a solvent. Well, we know in order to select a solvent, you want it to be what? Remember, so this is reasons to not select. Sorry, what am I saying? We're going to write down reasons why we would select a solvent. So we would select a solvent if it's insoluble at room temp, and then soluble at boiling, and then precipitate forms in ice water bath. Right? Those are kind of the 3 requirements we're looking at when we do these kinds of questions. So these are reasons why we would select a solvent. They want to ask us why not select a solvent. So A, the solvent took too long to boil. That is you just being impatient. That has nothing to do with the chemical effects of the experiment, right? So that's no, sorry. You might have noticed with water, because it has such a high boiling point, it probably took a little while to boil when you guys were actually running this on your own. So it's a little annoying. All right. B, benzoic acid was soluble at room temperature. That's great, right? That is a good reason why you should not select a solvent, which is what this question is asking for. We would prefer something that's insoluble at room temperature. So having something soluble at room temperature is not, yeah, that's why you would not pick that solvent, okay? Next, benzoic acid was not soluble when the solvent was boiling. Again, that's the opposite of what we said. We want it to be soluble at boiling. B and C are looking pretty good. Benzoic acid dissolved when the solvent was hot. Excellent. And then it precipitated out of solution when the test tube was plunged into an ice water bath. Yeah, that's not what we want. Not at all. Okay, so D is no good. Right? D is something that we would want to happen. Here we want things that we shouldn't want to happen. Is this making sense? I feel like it's reverse logic. It's kind of messing with my head a little bit when I say it. Basically, we want the opposites of these. Okay, these are good things. We want things that are valid reasons for not selecting a solvent. So insoluble at room temp is good. Soluble at room temp is bad. So that's valid. That's why we're not going to pick that guy. Okay. Soluble at boiling point. This dude, benzoic acid, not soluble at boiling point. That's a good reason to not select that solvent. That's crap. D is the ideal scenario. That's this guy. It's not the opposite of that guy. And then E, solvent would require the use of a water bath during large-scale crystallization. It is. So that's, yeah, that's correct. So B and C are valid reasons for not selecting a certain solvent. Okay, I hope I didn't mix you up there. All right, let's continue to the next one. Solid is being, pause, try it out, then we'll do it. Okay, a solid is being collected by vacuum filtration during a Chem 327 lab session. If a student wishes to wash the solid, what would be the correct sequence of events? All right, so we have 5 steps. Looking at the answer choices right off the bat, I don't have to use all 5. So that's good. So we are talking specifically about the wash step. So just off the top of my head, things I remember from the wash step is the first step is always to open the vacuum, right? The pinch clamp. And the last step is always to close the vacuum, right? So close it with the pinch clamp. So let's start there. So let's go first all the way to last. So number 1 says to bend the air inlet hose and close it with a pinch clamp. Well, closing the vacuum is our last step. So that would be 1. 2 is to add cold solvent. I don't know where it's going to go yet, but I do like that step. So I'm going to put a check mark next to it. 3, remove the pinch clamp to break the vacuum. Excellent. That's my first step. Right, want to break the vacuum open. 4, stir with a spatula. I like that one. Don't know where it goes, but I want to use it. And 5, add hot solvent in small portions. That's a bad one. Remember what happens if you use hot solvent and vacuum filtration to wash your crystals? You're just redissolving your crystals, right? You just undid your ice water bath step. So we definitely don't want to use 5. So we are breaking the vacuum, and then we have to either add cold solvent or stir it with a spatula. So our next step is you want to add the cold solvent. Once the cold solvent is added, stir it with a spatula to wash those crystals, and then go ahead and close the vacuum, have that system running again, okay? So this is 3, 2, 4, 1. 3, 2, 4, 1, D. Excellent. Let's try the next one. Pause, try it out, and then we'll run through it together. All right, so during the crystallization experiment, Constantine performed a large-scale crystallization using 0.400 grams of crude benzoic acid. He was determined to obtain a percent recovery of at least 80%. How much pure benzoic acid does he need to achieve 80% recovery? Do y'all remember the formula we used in the previous question? Pure over crude times 100%. We are looking for pure. We are given crude and the percentage. So all we're going to do is set this up. Pure is X. Crude is 0.400 grams. Percent is 0.80. Cross multiply. And you get X is equal to 0.80 times 0.400. So X is equal to 0.32 grams. So you want 32 grams of pure benzoic acid to achieve 80% recovery. Okay. I like these mathy ones personally. I don't think they're all so bad. I honestly love a mathy one. All right. Let's go for another one that's really wordy. Don't you guys like it? I'm kind of like, I tried to break up the table questions because some of the giant tables, oh my goodness, they give me a headache. So I tried to break them up for you. I hope this is helping. I really do. I feel like when someone explains the questions, it makes it a lot easier to get them sometimes. And it just like lets you know what mindset to be in. I love it. It's like because of my background, my hands like cut off. So they slightly disappear. It's great. Okay. Too much coffee. Anyways, pause, try it. We'll run through it. All right, the table below shows the results of solubility trials with 4 solvents of compound X. Woohoo! A water bath was kept at about 80 degrees Celsius to heat test tubes. Use the following table to answer problems 1 and 2. All right, let's take a look at what we got. 95% ethanol, boiling point 78. Room temp, insoluble. Water bath, soluble. Cold, precipitate. Hey, you guys see that? If we've learned anything in the past hour, it's that this is the ideal scenario, man. That's the best of the best. Insoluble, soluble, precipitate. Those are the 3 words I like to hear in that order. Excellent. Hexanes, we got insoluble, insoluble. Hexane's garbage. Dichloromethane, 40 degrees Celsius is our boiling point, and it was soluble at room temp, so bye. Those guys are awful. And then toluene has a boiling point of 111 degrees Celsius. It was insoluble at room temp, and it was insoluble in the water bath. You guys see an issue with that? How heated was our water bath? 80 degrees Celsius, right? So was it hot enough to bring toluene to its boiling point? No, right? Okay, just an observation. You know, when I ask you guys these questions, I feel like I'm like Dora the Explorer. It's like, how do we get to the mountain? Right. And that's how I feel when I do these, but I feel like it helps you guys out. Okay. Anyways, the question saying, based on these results, which solvent would be best suitable for crystallization? Well, we answered that already. We looked at the table, 95% ethanol. That's like a win-win situation. 95% ethanol wins the day. Excellent. That's 3 points in my pocket. Number 2, for which solvents are the results of the solubility trials inconclusive? Didn't we kind of answer this already? Right? We made a really good observation, and I think that's the answer. So it's inconclusive for which solvent? Toluene. Make sure I spell it correctly. Toluene, because the water bath wasn't hot enough, right? So because the boiling point is higher than the temperature of the water bath. So it's unknown if toluene will boil. Once again, I apologize for my handwriting. I know it's awful. All right, so that's clear. That's concise. That works for me. So we said toluene, right? The water bath is not hot enough. Okay. Excellent. I think we only got a couple left, so let's bang them out, shall we? Go ahead, try this one out, and then we'll run through it together. Already, TA conducted a large-scale crystallization of compound Y successfully several times. Good for that TA. I'm proud. The average percent recovery was 70%. The TA wants to obtain 5 grams of pure Y in a future crystallization. How much crude should she begin with? Okay, you guys see how they turn the tables on us here? Kind of interesting. So in this case, we're actually given the percent recovery, and we're given the grams of pure. They want crude. So remember, it's pure over crude times 100%. So in this case, we have the pure. The pure is 5 grams. Crude is, what is it, Y? We could use Y. Yeah, crude Y equals 0.70. So now you got to get fancy with the math a little bit. 0.70y is equal to 5.0. You have to divide by 0.7 on both sides. So y ends up being 7.14 grams. Now, let's say you didn't really read it, okay, or you did the math wrong. Let's think about it for a moment. You want 5 grams of pure Y, right? So your crude value has to be higher than your pure value, right? Your crude number is always higher because you're getting rid of those impurities. So your weight is going to be less when it comes down to the pure. Okay, so crude should always be higher than pure when it comes to numbers. All right. Alrighty, everybody. We only have one question left. And like I previously said in the beginning, I will have the second half of this review up by mid-Saturday afternoon. Okay, and then you have until Tuesday to study. So it gives you ample time to try the material on your own and then get kind of a refresher course. All right, so pause, try it out, and then we'll run through it. Alrighty, select the true statements concerning the washing step towards the end of the crystallization procedure. You know, I'm really starting to think he likes the washing step in this experiment. We've done a bunch of these. Oh my goodness. If you guys don't know that the washing step gets rid of soluble impurities by now, I don't know what to do. All right, let's see what we got. Number 1, the washing solvent should be cold to minimize redissolving the crystallized product. I really like that one. I hope you guys like that one. That looks like a good one. I'm gonna keep it. Oh, we can select multiple statements. So I'm gonna give it the circle of approval. The purpose of this step is to remove impurities that are soluble in the crystallizing solvent. Hey, ding, 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 we have a winner. I like that one too. The purpose of this step is to remove both soluble and insoluble impurities. No, that's not going to happen, right? We definitely don't want that one to happen because the insoluble impurities, these guys, these were removed during hot filtration. So 3 is wrong. And 4, before the washing step, the collected crystals should ideally be allowed to dry to expose the impurities. No, we dry after the washing step, right? Always wash step, then dry. So here you should have chosen A, 1 and 2. Alrighty, everybody, that's everything I have on the first 3 topics. I hope you found this helpful. If you have any questions at all, please feel free to email me. I'll clarify when I can. Enjoy the rest of your day. Study hard. You guys definitely have this theory quiz in the bag, okay? Have a good one, guys. Bye.